Hi, everyone. I'm hoping to join you for as much as the time as possible today. But since I'm dealing with conflict, I really appreciate the opportunity to be able to pre-record this short presentation. At the risk of sounding obnoxious, I'd like to start by quoting myself from a rant on the topic of stress drop more than 25 years ago in SRL, which opened with these lines. One of the most battle-weary parameters in seismology today is stress drop. Seismologists argue over everything about this parameter, including its name, meaning, measurement, and scaling with magnitude. If stress drop was battle-weary 25 years ago, it now must be feeling positively vanquished, as a lot of these basic questions persist today. So I think this initiative to take another look at stress drop is still very timely. The question that I would ask is, why do you want to know stress drop? And what is it specifically that you want to measure? The original definition of stress drop, as you know, is a measure of final fault slip as a fraction of fault area. And so people who are interested in source processes on a gross level might be interested in that. More commonly, I think, though, when people are talking about stress, they're using it as a parameter that's expressing the corner frequency, typically within the context of an omega squared spectrum, where that corner frequency might be determined from an EGF method, such as some of the ones that have been used in this project to date, often with the Madariaga definition of stress drop. But the corner frequency has also been related to a stress drop or parameter by the Bruhn model using a different constant K, which causes a difference of about a factor of 5 on the stress. The Bruhn version of the model is the one that's most frequently used in engineering seismology. It's rooted in Aki's omega squared spectrum, and it relates the stress drop to the high frequency ground motion. In particular, the Bruhn model relates the radiated spectral amplitude, the Fourier spectrum of acceleration, to two parameters, the seismic moment and the stress drop, which has been dubbed the Bruhn stress parameter by Bohr. And under Bruhn's model, the Fourier amplitude spectrum at high frequencies scales as moment to the 1/3, stress drop to the 2/3. Engineering interest in stress drop and in this model really took off in the late 1970s and early 1980s when Hanks and McGuire and Bohr showed that when you combine this model with equations from random process theory, which basically treat ground motion as Gaussian noise that has an underlying Fourier spectrum, then we can predict the observed ground motions, peak acceleration, the velocity, and the response spectra, which are what engineers are interested in. And it's been shown that that basic idea works in California if you assume an average stress drop of around 100 bars, or if you use a higher stress, it also works in the East. So since that time, the use of this so-called stochastic model in concert with the Bruhn stress parameter as the source parameter that's controlling the high frequency ground motion has become one of the most widely used tools for developing ground motion models for engineering applications, building codes, specific projects, and so on, especially in regions where the data are sparse for the large events close distance that are most interesting for engineers. What I'm interested in measuring when I talk about stress drop is the stress parameter that will predict ground motion amplitudes. That might include acceleration and velocity, which has limited interest, Fourier amplitude spectra, which have more interest, and of most interest still in the engineering community is response spectra. The reason why is to develop those ground motion models for use in seismic hazard analyses. And a very important caveat is that that stress parameter has to be combined with compatible path and site models and empirically validated. So what's needed in order to do that are Fourier amplitude spectra, or Fourier spectral amplitudes, and response spectral amplitudes that can then be used to invert models to find best fit stress parameter. And that model can then be demonstrably tied to ground motion measures of engineering relevance. Might also be noted that that inverted stress parameter can also be compared to those inferred from other methods, such as EGF methods and so on, in a few papers that have been published to date. So bottom line is that the right stress parameter model can predict the ground motions needed for seismic hazard assessment. And I think that is a topic of fundamental interest in engineering seismology.